So good afternoon, and thank you very much for being here at this presentation on methods for characterization of orbiting objects and space traffic management. Although I will focus on the characterization part because most of the time has been devoted to it. The presentation starts with a brief introduction, followed by the methodology used to characterize space objects from photometric measurements. And then I will present a test case in which this methodology is applied. And finally, I will summarize the main conclusions and the potential lines for future work. Okay, due to the exponential increase in space traffic over the past decade, and consequently in space debris, knowing the orbit of space objects is no longer sufficient to protect space assets and preserve the space environment. Therefore, we need to extend additional space surveillance activities to estimate additional parameters, like attitude and shape, the size, or the optical properties. This holistic characterization has many applications in this context. For example, in the design of active debris removal missions, or the improvement of atmospheric relative predictions, or collision probability estimations. Here we can see, the objective of this work is to estimate the attitude of an uncontrolled object from photometric measurements taken by a telescope. Here we can see a light curve which shows the evolution of the apparent magnitude over time as the object rotates and as the geometry between the sun, the object, and the sensor changes over time. Due to the strong coupling between different parameters that plays a role in this problem, a typical assumption is the knowledge of the geometry of the object, as well as the aerosol optical depth. Even under these assumptions, the problem shows a significant ambiguity in the measurement, meaning that different attitudes can provide equivalent light curves or photometric measurements. And additional problem is the existence of a heavily nonlinear measurement model. EMV has previous experience on has previously analyzed other estimation techniques like the least squares method or the asymmetric Kalman filter. However, these methods rely on an initial estimate and tend to converge to local optima near those estimates. This is the reason why we have decided to investigate Monte Carlo sampling methods in this work. The Bayesian inference method that is presented in this work is based on adaptive importance sampling principles. The objective is to approximate the target probability density function, which is unknown, using or drawing samples from a proposal distribution. And the adaptive importance sampling process adapts or refines iteratively this proposal distribution to match the target one according to a quality metric of the particles. In addition, we use a batch processing of the real measurements in order to reduce the occurrence of local optima. To that end, the light curve is divided into subtracts, and in each iteration, we process all the measurements of a subtract. And the weight of a particle is computed from the weighted root mean square error. In addition, we also perform an adaptive particle allocation in the first iterations in order to move particles from that have very low weight to regions of more interest that have higher probability density. And this way we can refine the initial proposal distribution. And the updates of the particle is based on two techniques. The first one is resampling, which is used to avoid the degeneracy of particles. And it basically removes particles that have very low weight and replicates those with a higher probability. And resampling is performed in combination with particle sum optimization, which is an efficient way of simulating or estimating the target PDF implicitly, without the need of explicitly computing it at each iteration. In addition, it's a good way of introducing diversity between the particles. Considering the inertia of the particles, the personal best, and the global optima of the swarm, we can accelerate convergence towards the true solution. Now let me explain the test case that is presented in this work. As commented before, a typical assumption is the knowledge of the geometry of the object, of the physical properties as well. And we also assume that over the tracking period, it follows a spinning attitude law. A spinning attitude law can be characterized by the orientation of the platform, which can be defined by three Euler angles, yaw, pitch, and roll, and by the orientation of the spin axis, characterized by azimuth and elevation, and of the spinning period. In addition, we assume knowledge of the aerosol optical depth, and that the inertial period is approximately equal to the apparent one that can be computed using other period finding algorithms. Here we can see that the light curve produced by this simple model consisting of the platform and the solar array for that sensor noise level and for that attitude, reference attitude. Now we can take a look at the execution of the filter. The plots show the distribution of particles at the different iterations, and the size of the marker is related to the weight of the particle, and the true attitude on the reference one is represented with a red cross. You can see that we start with a uniform distribution because we have no previous knowledge of the attitude. After the first initial adaptive particle location, we see that some higher probability regions are already identified, and in the subsequent iteration, we see how particles converge to the true solution and to another one, until we reach the last iteration where the posterior probability density function is more refined. Then we perform a cluster analysis to identify the modes of this PDF and obtain, as you can see in the table, the weighted state and the weighted standard deviation of each candidate solution. If we simulate the light curve for these two solutions, we see in the plots that they closely align the real or the reference photometric measurements. This is not a limitation or a problem of the method, but rather is a consequence of the ambiguity of the light curve immersion problem. We have two solutions that are equivalent, and in fact the method must be robust and must ensure that all the valid solutions are identified. Finally, let me summarize the main conclusions. In this first part of my PhD, we have been able to understand the challenges of light curve immersion problem for attitude estimation. We analyzed the limitations and the advantages and limitations of traditional methods like least squares method or uncertain Kalman filter, sequential particle filters, and we have developed a robust, accurate, and computationally efficient methodology to based on Bayesian inference to solve this to solve at least the attitude from light curves. And potential lines of future work include the improvement of the accuracy estimation, the estimation of the optical properties and of the aerosol optical depth together with the attitude of the object, and also analyze 3-axis stabilized satellites, which are more challenging because the variability of the photometric measurements is lower and there is more ambiguity. And also finally extend the analysis to using real light curves. Finally, you can see here a summary of the main achievements over this year. The paper presented at the International Astronomical Congress is related to the other part, the part of the space traffic management. And in that paper, we propose a method to design maneuvers in which the maneuver cost is distributed between the two satellites in collision curves. This distribution of the maneuver cost is based on the contribution of each one to the collision risk. And the rest of papers are based on, well, this attitude estimation method, and some of them include the first efforts in estimation, or for the estimation of the optical properties together with the attitude. So thank you very much for your attention, and all the best.